All right, let's dive into something pretty wild today, the world of quantum computing. We're going to talk about how you can actually simulate a quantum computer on the laptop or desktop you're using right now, all thanks to an incredible open source project called Qrack.
But first, let's start with a bit of a brain teaser. We all know that huge, powerful, error-corrected quantum computers, well, they aren't really here yet. So how in the world are scientists and programmers supposed to build the software for them? It's a total chicken and egg problem, right? You can't write the programs without the computer, but you can't build the computer without knowing what kind of programs it needs to run.
And just to give you a sense of the scale we're talking about, look at this number, 4.5 petabytes. That is the insane amount of regular computer memory you would need to perfectly simulate just 48 quantum bits. To put that into perspective, we're talking about the combined RAM of thousands of high-end computers, all just to handle a tiny quantum system. This is a massive, massive challenge.
So, how do we get around this paradox? Well, the answer is through really clever software simulators. These are the tools that let us build a bridge to that quantum future, and it's frameworks like Qrack that are really paving the way.
So, you might be asking, why go to all this trouble? Well, simulators are absolutely essential right now. They let us design, test, and completely debug quantum algorithms long before the real hardware is ready to go. They also give us a kind of perfect answer key to check the results we're getting from today's early and, let's be honest, kind of noisy quantum computers. This just speeds up the whole research and development cycle. And sometimes it even helps us discover new quantum-inspired tricks for the classical computers we already have.
Okay, so let's get into the nitty-gritty of the problem. We saw that staggering 4.5 petabyte number, but where does it actually come from? Understanding this is the key to really appreciating just how smart these simulators have to be. It all boils down to this thing called the state vector. Think about it like this. A normal computer bit is simple, right? It's a 0 or a 1. But a quantum bit, a qubit, can be a combination of both at the same time through superposition. So to keep track of every possible outcome in a system of n qubits, a classical computer has to store this gigantic list of complex numbers. That list, the complete description of the quantum state, that's the state vector.
And this is the killer. For every single qubit you add, the size of that state vector, the amount of memory you need, literally doubles. It's not a straight line up. It's an explosion. This exponential growth is why the memory requirements just go completely off the rails so quickly. And this chart just shows you what that looks like in the real world. At 20 qubits, you need about 17 megabytes of RAM. No big deal, your phone can handle that. But jump to 30 qubits and suddenly you're at 17 terabytes. Okay, a beefy gaming PC. But push it to 40 qubits and you're at over 17 terabytes of RAM. It just becomes unmanageable almost instantly.
So it's really important to separate two different things here. The number of qubits tells you how much RAM you need. That's the storage for the giant state vector. But the speed of your simulation, how fast you can actually run the quantum gates, depends on your processing power, like the thousands of little cores on a graphics card that do the number crunching. To do this well, you need a ton of both.
So if a brute force approach is just astronomically expensive, there has to be a better way, right? Of course. This is where the simulator itself has to be intelligent. It's not about throwing more hardware at the problem. It's about simulating smarter, not harder.
And this quote right here, it really gets to the heart of what makes Qrack so special. It's not just a single tool. It's more like a whole toolbox. It actually looks at the quantum circuit you give it and figures out the most efficient, the cheapest way to simulate it, dodging that exponential bullet whenever it can.
One of its most powerful tricks is something called Schmidt decomposition. And the idea behind it is actually pretty simple, but it's brilliant. If you have groups of qubits that aren't quantumly linked or entangled with each other, why on earth would you simulate them as one giant expensive system? Instead, Qrack is smart enough to simulate each little group on its own, which is exponentially cheaper. It only bothers to combine them into the full complex simulation at the exact moment a gate forces them to get entangled. It's so clever. And the results are just wow. Using techniques like that, Qrack can do things like simulate a special 60-qubit state, a task that would be flat out impossible for a normal simulator. A 60-qubit simulation would require more RAM than we have on the entire planet. But because Qrack is smart about it, it finds a way.
And this intelligence isn't just locked away in one library. Over time, Qrack has grown into a whole universe of tools that all work together, creating a complete solution for anyone doing quantum R&D.
This table lays it all out. You've got the core, which is Qrack itself, the super fast engine written in C++. Then, for pretty much everyone else, you have PyQrack, which is the easy-to-use Python version. And on top of that, you have specialized tools like PyQrack for specific optimization problems, and TheoremInQ, which is a whole platform for running huge simulation experiments. It really is a complete toolkit.
Let's just focus on PyQrack for a second, because it really is the most important bridge for the community. It takes all that high-performance C++ power and makes it available in Python, which is, where most of the quantum research community lives. And it plugs right into the big frameworks people are already using, Qiskit, PennyLane, Cirq. So you get all the speed of Qrack without having to change your entire workflow.
Okay, so after hearing all that, you might be thinking, this sounds incredible, but also incredibly complicated. But the great thing is, the project is built from the ground up to be open and welcoming to new people who want to get involved. And it all starts with the standard open source playbook on GitHub. You just fork the project to make your own copy, clone it down to your computer, make your changes in a new branch, and then you open up a pull request to suggest merging your improvements back into the main project. It's the collaborative process that makes all of open source work. And you absolutely do not have to be a C++ genius to help out. There's what they call a ladder of contribution. You can start as a total beginner just by fixing typos or clarifying things in the documentation. From there, maybe you help with one of the Python plugins, then the main PyQrack wrapper itself, and then eventually, if you become an expert, you can contribute to the core C++ engine. There's a spot for everyone at every skill level.
So what's the first step? It's super simple. First, head over to GitHub and check out the PyQrack examples repository. It's the best way to just get your hands dirty with the code. And second, join the Advanced Computing Topics Discord server. That's where the community hangs out, asks questions, and where you can connect with the developers directly.
Which kind of leaves us with one last big question to think about. We always imagine that progress means waiting for better hardware. But what if that's not the whole story? Could it be that the really clever software we're building today, these intelligent, optimizing simulators like Qrack, are the actual keys that are going to unlock the door to the quantum age? Something to think about. Thanks for tuning in.